In dynamics, when we want to study an object's motion, we look at its mass and its velocity. Multiplying them together, we call their product momentum. Imagine this. What's more painful, getting hit by a ball moving at 20 meters per second or a truck moving at 20 meters per second? Of course, the truck's more painful. Although they have the same speed, the truck is heavier than the ball, so it has more momentum and is way more painful. Now consider this. Would it be more painful to get hit by a ball moving at 2 meters per second or 30 meters per second? Though they have the same mass, the second ball moves faster, has more momentum, so it would be more painful. Now in most situations, object's mass stays the same, while their velocity often changes. When the velocity of an object changes, its momentum changes too. An object's momentum changes when a force is exerted on it. These are related by the impulse momentum theorem. This theorem says that the amount of force applied over a certain time yields the change in momentum, which we call impulse. Almost all forces vary over time. Thus, simple multiplication is no longer enough to determine the momentum. This is where the integral comes in. If we think about it, impulse is simply the sum of forces applied over infinitesimal time periods. As we increase the number of time periods, the better our measurement becomes. We say that the integral from a to b of the force function is equal to the impulse. The concepts of force and momentum are crucial in analyzing situations. Let's say that while analyzing a recent collision along S-legs, experts' calculations say that the truck exerted a force modeled by f of x is equal to 6,262.6 times cosine of 4x plus 1 newtons from a time of 0 until time equals 0.7854. From the CCTV footage, a car of 1,000 kilograms skidded off at 120 kilometers per hour while the truck left the collision at 55.5 kilometers per hour. S-legs has a speed limit of 80 kilometers per hour, and assuming an ideal collision was either the car or the truck overspeeding. The graph plots force over time. Here, the shaded area is the change in momentum. We integrate the force function to find the change in momentum. By integrating, we find that the momentum the truck imparted to the car was 5,004.4 km per second. When dealing with an ideal collision, this means that the momentum is conserved. Thus, we come up with the following formula. The momentum the car gains is equal to the momentum that the truck loses. We can use this to find the initial velocities of the vehicles. Knowing the car's final momentum and how much momentum it gained, we can find the initial momentum and velocity as such. A similar process can be done for the truck as shown. Thus, the car was far over the speed limit while the truck was not. We conclude that it is the car's driver at fault. Concepts like momentum and force play crucial roles in analyzing collisions, which serve an important part in road safety and security. Physicists rely on calculus to accurately reconstruct the situation, and this shows how important integration is in solving a variety of problems in sciences and in everyday life.